This is not simple. We need to have multiple rockets launching in a coordinated fashion such that we can all meet up together in space at the same time and place.
It's awesome to see how smoothly Artemis II went, but now the real challenge begins. Every Artemis mission after this has to deal with a pretty massive hurdle: orbital refueling, and the huge, still uncertain number of tanker flights needed to fully fuel the lunar lander. That means a lot of launches, a lot of coordination, and plenty of room for things to go wrong. But here's the interesting part. What if that number could be cut way down? According to Elon Musk, SpaceX might already have a solution that could reduce the required tanker flights by more than half. As I mentioned earlier, one of the big things NASA wants to focus on in the very near future is proving they can actually pull off a multi-launch campaign. And that's no small task. You're talking about multiple rockets lifting off at just the right times, all meeting up in space at the exact same place. It's basically orbital choreography. Now add Starship into the mix. It's huge, with a dry mass of around 606,000 pounds, 275 metric tons. The current plan is to launch a bunch of Starship tankers into orbit, have them dock, and transfer fuel to a propellant depot waiting in space. Then the Human Landing System, HLS, version of Starship shows up, fills its tanks, and heads off toward the moon. No one knows the exact number yet, but estimates suggest it could take somewhere between 16 and 19 tanker launches just to fully refuel a single Starship. That's a lot of launches, and with that comes a lot of risk. And it's not just about coordination. There's also something called boil-off. These cryogenic fuels have to stay incredibly cold, and even small temperature changes can cause some of them to slowly evaporate. So not only do you need a ton of tanker flights, but you also need to launch them close together to minimize fuel loss. So obviously, if SpaceX is serious about building a lunar transport system, they need to cut down the number of tanker flights as much as possible. Because the more launches you need just to refuel one ship, the more complicated and expensive everything becomes. And Elon Musk recently dropped a pretty big hint about how they plan to fix that. He said on X that the Starship V4 tanker version could deliver more than 200 tons of propellant per flight, which would mean something like 5 or 6 tanker flights to refill a lunar transit Starship in orbit. And then he casually added that this shouldn't be a big deal if they're doing more than 10,000 flights per year. Now, if Starship V4 sounds new, that's because it is. This is the next big planned evolution after V2 and the upcoming V3 versions. It hasn't flown yet and is still in development planning, but it's expected to be a serious upgrade. We're talking about a much taller vehicle, possibly close to 150 meters, with a liftoff mass around 7,500 tons. The upper stage would be longer, meaning more propellant volume and a lot more capability overall. The goal with V4 is basically to push everything to the next level. In some reusable configurations, it could potentially send over 200 tons to orbit. That's huge. It would help with massive Starlink deployments, but more importantly, it would make Moon and Mars missions way more practical by reducing how many launches you need to assemble and refuel ships in orbit. One of the cool details about V4 is the engine count. The upper stage would add 3 more Vacuum Raptor engines, bringing the total for the full stack to 42 engines, with 33 on the booster and 9 on the ship. Musk joked that this was as foretold in the prophecy, which is a clear Hitchhiker's Guide to the Galaxy reference. In the book, 42 is the answer to life, the universe, and everything. It's classic Musk humor. But beyond the joke, 42 engines actually make sense from a performance standpoint as thrust levels, engine mass, and vehicle weight keep evolving. There's also talk of upgraded Raptors producing up to 300 tons of thrust each. If that happens, the booster alone could generate around 10,000 tons of liftoff thrust, roughly 3 times more than the Saturn V. That kind of power would support the bigger, heavier V4 design and allow it to carry a lot more propellant to orbit. And that's really the key point here. If each tanker can deliver over 200 tons of propellant, suddenly you're not talking about a dozen or more refueling launches. You're talking about 5 or 6. That makes orbital refueling feel a lot more manageable and moves the whole lunar mission architecture closer to something that actually looks scalable instead of insanely complicated. Maybe the real bottleneck here is just time. NASA is targeting Artemis III around 2028, so once orbital refueling is proven, they'll need a pretty quick demo. The demonstration lander will likely be V3 based, and NASA might insist that the operational lunar lander stays almost identical to that demo version to reduce risk. That's just how they operate. If something works, don't change it too much. NASA's human landing system, the moon version of Starship for Artemis, is obviously a high priority. But HLS is so different from the other variants that it almost feels like a parallel program. No heat shield, no atmospheric re-entry, totally different landing setup. It's still Starship, but also not really the same Starship. As for SpaceX, V3 seems to be the main focus right now. They're trying to get one core design flying reliably, build flight experience, test engines, deploy Starlink, and most importantly, prove orbital refueling works. They're not rushing into a bunch of specialized versions yet. The goal at the moment is simple: make the system work consistently. So, at least for the Moon program, it probably makes sense to stay close to V3 hardware instead of waiting for V4, especially if NASA wants stability and minimal design changes to lower risk. And I think Elon has thought about this too. He specifically mentioned that a V4 tanker could deliver more than 200 tons of propellant per flight. So maybe the Artemis HLS gets frozen at V3 to satisfy NASA, but ends up being refueled by V4 tankers. That actually sounds like a pretty logical compromise. One question though, do you think a V3 ship could stack on a V4 booster? That would be pretty cool if they could mix and match like that. Let me know what you think. If nothing changes in the plan, SpaceX's Starship propellant transfer demo is supposed to happen this year. And yeah, doing this at this scale has never been done before. But it's not like they're going in blind. A lot of groundwork has been laid over the past few years. Back in 2020, NASA awarded SpaceX a tipping point contract specifically to prove that Starship could transfer liquid oxygen, LOX, in space from one tank to another. The challenge is that liquid oxygen is extremely cold, cryogenic, and behaves very differently in space. In low gravity, liquids don't settle at the bottom of a tank as they do on Earth. Instead, they float around, mix with vapor, and can form what's called two-phase flow, liquid plus gas together. If gas gets sucked into the transfer line instead of pure liquid, called vapor pull-through, it can disrupt the transfer process. On Starship's third test flight on March 14, 2024, SpaceX successfully demonstrated this in-space propellant transfer. They moved liquid oxygen from a smaller header tank near the nose of the vehicle to the large main oxygen tank at the bottom. The transfer was driven mainly by pressurizing the header tank, which created a pressure difference that pushed the liquid through a transfer line. To prevent vapor from entering the line, they used a tiny acceleration, called settling acceleration, to gently push the liquid to one side of the tank, so it stayed properly positioned. A valve and a specially sized orifice controlled the flow rate so the correct amount of oxygen moved within the planned time, and the whole transfer took less than 100 seconds. Before the flight, NASA and SpaceX ran extensive simulations. They used system-level thermal fluid models and high-fidelity CFD, computational fluid dynamics, simulations to predict how the liquid and vapor would behave. These models included heat transfer between tank walls and propellant, pressure changes, turbulence, surface tension effects, and even sloshing caused by vehicle motion. They also modeled helium pressurant gas added to maintain pressure. After the flight, they compared the simulation predictions to actual flight data from sensors. The results matched closely. The models correctly predicted that liquid, not vapor, would be transferred, and that the pressure behavior would stay within safe limits. The CFD simulations also showed that even very small accelerations in space were enough to keep the liquid properly settled during transfer. In short, this test proved that Starship can move super cold rocket fuel between tanks in microgravity, and that NASA's predictive models were accurate. The upcoming 2026 Starship ship-to-ship propellant transfer demo will begin with 2 launches from SpaceX's Starbase in Boca Chica, Texas. The first launch sends up a Starship tanker variant stacked on top of a fully reusable Super Heavy booster. At liftoff, all 33 sea-level Raptor engines ignite at once, producing about 7,500 metric tons of thrust using liquid methane and liquid oxygen. The vehicle ascends over the Gulf toward low Earth orbit. About 169 seconds after launch, the stages separate using hot staging. The Super Heavy booster throttles down to 3 center engines, while the upper stage Starship ignites all 6 of its Raptors, 3 optimized for sea level and 3 for vacuum. The tanker Starship, carrying roughly 1,500 metric tons of propellant, continues to orbit. Meanwhile, the booster performs a boost-back burn and then a landing burn. SpaceX will attempt to catch it with the Mechazilla tower arms at Starbase. If that fails, it will make a controlled splashdown in the Gulf. 3 to 4 weeks later, a second Starship tanker, called the Chaser, launches on a similar trajectory and enters orbit to rendezvous with the first vehicle, now serving as the target. In orbit, the target Starship spends several weeks testing how its propulsion system, tanks, and insulation handle long-duration exposure to space, including propellant boil-off. When the Chaser arrives, it autonomously navigates toward the target using advanced sensors derived from SpaceX's Dragon spacecraft technology. The two vehicles perform precise station-keeping maneuvers in microgravity before docking using SpaceX's androgynous docking system, which allows either vehicle to act as the active partner. Once docked, the Chaser transfers more than 10 metric tons of liquid oxygen to the target through cryogenic-rated plumbing, quick disconnects, and couplers designed for space operations. The transfer relies on key techniques such as propellant settling, autogenous pressurization, and managing high fill tanks in microgravity. This builds on earlier in-flight demonstrations that successfully moved propellant internally within a single Starship. This test is a crucial step toward full orbital refueling. For a Mars mission, a Starship would launch to orbit and then dock multiple times with tanker variants, gradually filling its methane and oxygen tanks before performing a trans-Mars injection burn. After the transfer is complete, the ships undock and perform separate deorbit burns. Each re-enters Earth's atmosphere and targets a controlled splashdown zone, likely in the Indian Ocean. Throughout the mission, continuous telemetry collects data on fluid behavior, pressure control, docking loads, and re-entry performance, helping refine future refueling systems for lunar and Mars missions.